We talked about conjugate pairs on Tuesday, but I'm not sure that we fully wrapped our mind around what conjugate pairs were on Tuesday. So I want to go back and review this. You can take a picture of it. You can do whatever you want to with it. What I want you to understand about conjugate pairs is if I have a solution, or if I have a zero to a polynomial, and one of my zeros is 4i, okay? If one of my zeros is 4i, a conjugate pair means that I have to have its opposite. So I have to have negative 4i. Complex solutions travel in pairs. Now, rational solutions don't. You can have positive 2 as a solution, and positive 3 as a solution, and you're not going to have their opposites. But if it's a complex zero, they travel together. Okay? And the reason is because when you multiply those out, it becomes a real number. Okay? So complex zeros always travel in pairs. It might also look like this. Okay? Sometimes when you're doing the quadratic equation or you're using completing the square, you may get a zero that looks like 2 plus 3i. The conjugate pair with that is 2 minus 3i. And you've gotten complex and irrational solutions before, but they typically, when you're doing it, you end up looking at something like this, plus or minus 4i. What I want you to realize is that if you end up with an answer like plus or minus 4i, you have two different answers. You have plus 4i and you have minus 4i. Okay? When you're doing the quadratic formula, you may end up with 2 plus or minus 3i. Okay? You need to realize that that's two different solutions, 2 plus 3i and 2 minus 3i. Okay? Now, this particular screen is not talking about this, but the same is also true for irrational solutions. Okay? So if I have the square root of 3 as a solution, what do I also have? Negative square root of 3. And again, very, very often it shows up looking like this because we're either using the quadratic formula or we're using completing the square. So we can end up with that plus or minus square root of 3. And it's super, super important that you realize that that plus or minus, that's giving you two different answers. So conjugate pairs occur when we have a complex, so it occurs when we have a complex zero or when we have an irrational zero. Okay, rational zeros do not necessarily have its opposite, but complex zero and irrational zeros do. Okay? Can I move off the screen? Am I good? Okay. Now what I want you to do is I'm going to give you 3 minutes. 3 minutes. And I want you to find all the zeros to this. Now, remember, if I don't know what to start with, I start with factors of this right here. Okay? So that could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 12, plus or minus 15. I'm almost done, right? Plus or minus 20, plus or minus 30, and plus or minus 60. Okay, now I know that's a lot. I know that's a lot. I always start at plus or minus 1 or plus or minus 2. Okay? So start there and see if you can find the zeros. It takes a little bit of time to find this first zero. For this particular one, it takes a little bit of time to find this first zero. What some students do is they put this into Desmos, okay? Then when you put this graph into Desmos, you can look at it and you can see where the graph crosses the x-axis, okay? And then that really tells you where you can start with your zeros. What is the problem with that method? You can't do that on a test. Okay, you can't use Desmos on your test. Okay? So now I do write the test. The good news is that you will not have a negative 60 on the test. But I like to do this one now so that you can see what it consists of when you don't know where to start. So I'm going to start with positive 1. I'm going to start with positive 1. Okay, and I'm going to see if that works. I'm going to see if positive 1 works. So I bring down my 1. 1 times 1 is 1. And I'm left with negative 2. 1 times negative 2 is negative 2. 6 and negative 2 give me 4. 1 times 4 is 4. 2 plus 4 is 6. 1 times 6 is 6. And it doesn't work. How do I know it doesn't work? Because I've got the remainder. Good. Got the remainder. Okay. So I'm going to start over with something else. So I'm going to go with negative 1. Negative 1. Okay. I bring down the 1. Negative 1 times 1 is negative 1. Negative 3 and negative 1 is negative 4. Negative 1 times negative 4 is positive 4. 6 plus 4 is 10. Negative 1 times 10 is negative 10. 2 plus negative 10 is negative 8. Negative 1 times negative 8 is positive 8. Does it work? No, because I have a remainder. So that doesn't work either. Okay. So now I'm at number 2. So I start with 2. I bring down the 1. 2 times 1 is 2. Negative 3 plus 2 is negative 1. 2 times negative 1 is negative 2. 6 and negative 2 is positive 4. 2 times 4 is 8. Does it work? Does it work? No, I have a remainder. It doesn't work. So just when you think that you're going to go crazy, we're going to do -2. Okay? So I bring down +1. -2 times 1 is -2. -3 plus -2 is -5. -2 times -5 is +10. 6 plus 10 is 16. -2 times 16 is -32. That's a 2 right there. I just erased a little bit of it. 2 plus -32 is -30. -2 times -30 is +60. And -2 works. Now, what you have to remember. So one of my zeros is -2. Sometimes students forget that first 0. And then they start factoring and they think that's the only 0. Okay, they forget that first 0. How many zeros am I looking for total? 4. Why? That's the highest exponent. So I'm looking for 4 total. Now multiplicities might be involved. I may have some irrational solutions and I may have some complex solutions, but I'm looking for 4 total. Okay? If -2 is a solution, what's my factor? X plus 2. Okay? So now I've got 1x to the third minus x squared plus 16x minus 30. So I get very hopeful that maybe I can factor this by grouping. Okay, so I pull out an x squared with those first 2 terms. Then I try to pull something out of the second 2 terms, and what happens? Can I factor it? No, you can't factor it. Okay, so what am I back to? Synthetic division. Okay, so I'm back to synthetic division. Now, the good news is I've already tried plus or minus 1 and it didn't work. There's no reason for me to try it again. Okay, I've already tried plus or minus 2. One of them did work, so I'm not going to try that one again. Okay, so now I'm going to start with +3. +3. I bring down my 1. 3 times 1 is 3. -5 and 3 is -2. 3 times -2 is -6. 16 and -6 is 10. 3 times 10 is 30. Did it work? Yes. So I have a +3 as a 0. What's my factor? If +3 is my 0, what's my factor? Good. X minus 3. Okay, now, what this means is 1x squared minus 2x plus 10. 1x squared minus 2x plus 10. So I'm hoping that I can find 2 numbers that multiply together and give me +10 and add together to give me -2. Am I able to do that? Yes?
If we get to that point and it is factorable, can we still do something?
Yes, ma'am. You can. The question was if it's factorable and you would rather use synthetic division, can you? And the answer to that is yes. Okay? This situation, it is not factorable. Okay? And it is a quadratic. So what do I have to use here? Quadratic formula, and I will tell you that most of my students prefer the quadratic formula. But you've seen me do the quadratic formula several times. So for this one, I'm going to do completing the square just so you can see me do it. Okay? So I'm going to do completing the square. So I've got 1x squared minus 2x plus 10. Now, if you prefer the quadratic formula, that's fine. This one is a nice one for completing the square. And what I define as nice for completing the square, my A value is 1 and my B value is even. Okay? That makes it nice. So, the first thing I'm going to do for completing the square is I'm going to move that 10 over. Okay, so I've got x squared minus 2x equals 10. Okay, how is that different? Nope, it's not minus, it's negative 10. So I've subtracted 10 from both sides, and I get negative 10 right here. Now, how is this different than when I'm trying to get to the vertex formula? When I'm trying to identify the vertex in a parabola, how is this process different than what I'm dealing with when I'm trying to get to the vertex? It's the equal sign, but what initially is it equal to? 0. Okay, when I'm trying to put it in vertex form, I'm equal to f of x. So I don't get to use both sides of the equation. When I'm solving, I'm able to use both sides of the equation. And that makes it a little bit easier. Okay? So here, my next step, I'm going to take half of negative 2. What is half of negative 2? Negative 1. And what is negative 1 squared? 1. So I'm going to add 1 right here, and then I'm going to add 1 right here. Okay? Now, the reason that I added 1 is because I'm dealing with both sides of the equation. When I'm trying to get it to the vertex form, I'm only dealing with one side of the equation. So I have to keep everything equal on one side. So at that point, I would add 1, and then I would subtract 1. But that's not what I'm doing here. I'm able to use both sides. So when I'm able to use both sides of my equation, then I just add the same thing to both sides. And that's what I've done here. Okay? My next step is to factor. So I'm left with x minus 1 squared. That's equal to negative 9. Now, at this point, I take the square root of both sides. And you are in the habit of saying plus or minus the square root of negative 9. Putting in that plus or minus right there immediately identifies that as two different answers. You're going to have plus square root of negative 9, and you're going to have minus the square root of negative 9. Okay? So that plus or minus means I'm no longer talking about one solution, I'm talking about two. And remember, they travel in pairs if the answer is irrational or the answer is complex. Okay? Now, I can simplify this to plus or minus 3i. The square root of the negative is I. The square root of 9 is 3. That's why I have plus or minus 3i. My next step is I add 1 to both sides, and I'm left with 1 plus or minus 3i. Now, you need to remember that that is two different answers. I'm completely fine if you leave it written as 1 plus or minus 3i. I don't have a problem with that at all. Okay? So I have 1 plus 3i. Then I have 1 minus 3i. So you certainly can write them separate or you can write them together as long as you identify that you're talking about two different answers. Then I've got my other two solutions. Don't forget about these. Negative 2, positive 3. Okay, so how many solutions do I have? 4. How many times does it cross the x-axis? 2. It only crosses the x-axis for real numbers. Complex solutions do not cross. Okay, so I'm going to write that down too. Okay, these two cross x-axis.
And how would you graph this?
Well, it only crosses in two places. Okay, So if we were graphing this, let me write this down and then I'll erase it and I'll show you how to graph it. Okay, these do not cross. Okay? So my real solutions cross the x-axis. My complex solutions do not. Do irrational solutions cross the x-axis? So that would be like the square root of 2, the square root of 3, 2 plus the square root of 3. Okay, I've got one yes. Irrational. Do they cross? Somebody said no. Okay, let me ask you this question. Are irrational solutions real? Yes. Remember that big thing that I had on the board? Irrational are real. Real solutions cross the x-axis. The only thing that doesn't cross the x-axis are the complex. Okay, so irrational solutions do cross the x-axis. Okay. The question was, how would I graph this? Okay, so I would graph this. Am I going same direction or opposite direction? What's my end behavior? Okay, think about end behavior. Okay, are they opposite directions or are they the same? Same. Tell me why. Good. At the highest exponent is even. Okay, so am I going both up or both down? Both up. Why? Because it's positive. Good. Okay, so we know that my end behavior is going to look something like this. Okay? That's my end behavior. Now, I know that I cross at -2 and +3. What is my y-intercept? 60. -60. So that is like way down here, like below the floor. Okay? So it's going to look something like this. Now there is going to be a little bit of weird behavior somewhere. We don't know exactly where, but those two complex solutions, and it occurs pretty close to the vertex of the, or not vertex, but the minimum. Okay? So this is what it would look like, because you know your y-intercept is way down there. Okay? That's a great question, though. Okay? Okay. Hopefully, doing multiple problems like this will help things come together for you. Okay? That's my hope. That's my hope. Okay? Can I go to the next screen? Okay, we're changing gears. Okay. This is what we call a rational function. This is a rational function. Okay, I do want to talk about rational functions. You will be asked to graph a rational function in your project towards the end of the semester. You are not asked to graph a rational function on your test because you don't have access to Desmos. Okay, so you will not be asked to graph a rational function on your test. The only things that you're asked to do on your test are to find the domain of a rational function, to identify the vertical and the horizontal asymptotes. Okay, so you're not graphing this, you're just telling me a little bit about it. So those are the things that you want to be aware of. The domain, vertical asymptotes, and horizontal asymptotes. So we're going to start with this one right here. Find the domain of the given function. Okay, this is called a rational function because we have x's in the denominator. We have variables in the denominator. That's what makes it a rational function. It's also what means we have to limit the domain. Why do we have to limit the domain? What's in the denominator? I have a possibility of zeros in the denominator. Okay? So my denominator, x squared minus x minus 2, cannot be what? Okay, but yes, that is correct. But that x squared minus x minus 2 can't be equal to what? 0. Excellent. Okay, so now can I factor this? Yes, I can factor this. Okay, so this factors to x minus 2 and x plus 1. Okay? That means that x minus 2 cannot be 0, and it means that x plus 1 cannot be 0. So x can't be 2, and x can't be negative 1. Now, I'm going to draw this on a number line because if you draw it on a number line, you are less likely to make a mistake when you put this in interval notation. And you do have to put this in interval notation. Okay? I'm going to put a circle here at negative 1 because x can't be negative 1. I'm also, nope, that's not negative 1, is it? This is negative 1. Okay? Then I'm going to put a circle right here at positive 2 because x can't be positive 2. Okay? Now, can x be anything down here? Yes. Can x be anything up here? And you guys do great at that. You almost always identify those two. However, can x be any of these? Yes. That's where students forget. So my domain for this is negative infinity to negative 1. Then I've got to address the negative 1 to the 2. So don't forget that part right there. Then I've got 2 to infinity. Okay? So that is the domain of this function. That is something that you will be asked to identify. The domain of a rational function. And you know how to do that. We've done that before. Okay? Can I go to the next screen? Yes? Okay. This is the graph of this. This is the graph of this. Now, just now on the screen before this, we identified that x cannot be negative 1 and that x cannot be positive 2. So I want you to look at this graph right here and tell me what is happening when x is negative 1 and when x is positive 2. What is happening? Say that again. My graph never crosses it. My graph never goes over positive 2. My graph never goes over x equals negative 1. Never, ever, ever. Because if it crossed that, I would have an x value of positive 2. And if I have an x value of positive 2, my function is undefined. Okay? So, these are what we call our vertical asymptotes. So our domain, the domain of a function, okay, and the domain is determined by the denominator. Okay? The domain of the function and the denominator of the function dictate and determine our vertical asymptotes. So my vertical asymptotes here, my vertical asymptotes are x equals to negative 1 and x equal to 2. Those are my vertical asymptotes. Okay, I want you to realize that my asymptotes are not part of the graph. My asymptotes are not part of the graph. They guide the graph. but they are not part of the graph. So my domain and my denominator determine our vertical asymptotes. Okay, whoops, I put x not equal to 2. My asymptotes are the line. So my two asymptotes are x equals -1 and x equals 2. That's what that means right there. Okay? Now, I want you to look at, can I erase all this? Can I erase this? Okay. Now what I want you to look at is I want you to look at the degree of my numerator. What is the degree of my numerator? 1. Okay, that's because my highest exponent in my numerator is 1. So the degree of my numerator is 1. What's the degree of my denominator? Okay, so in this situation right here, that is my horizontal asymptote. Okay? My horizontal asymptote, is dictated or determined by the relationship between numerator and denominator. So horizontal asymptote is determined by the relationship between the numerator and the denominator. Okay. In this situation, my numerator's degree is less than my denominator's degree. And this happens a lot. Okay? So my numerator, the degree of my numerator is less than the degree of my denominator. When that happens, your horizontal asymptote is the x-axis. So it's y equals 0. Okay? It's y equals 0. Now, did I cross the horizontal asymptote? In this graph, does this graph cross the horizontal asymptote? Yes. So it is okay to cross horizontal asymptote. You don't always cross it, but sometimes you do. Okay? It's okay to cross the horizontal asymptote. Okay. Now, the other thing that I want you to look at is I want you to look at the x-intercept and the y-intercept. Can I erase all this? Okay. So I want you to look at the x-intercept and the y-intercept here. The x-intercept and the y-intercept. Okay? I find my x-intercept. My x-intercept is when the numerator equals 0. Okay? So here, my numerator is just x, so x equals 0. That's my x-intercept. My y-intercept is when I plug 0 in for all the x's. Okay? So my y-intercept would be 0 over 0 squared minus 0 minus 2. So this is also my y-intercept. Okay. Now, I've got several screenshots that I would encourage you to take a picture of. Several screens that I would encourage you to take a picture of. Can I go to the next screen to do that? Okay, here is a summary of how to determine a horizontal asymptote. How to determine a horizontal asymptote. Okay? When the numerator and the denominator of a rational function have the same degree, the line y equals a over b is the horizontal asymptote, where a and b are the leading coefficients of the numerator and the denominator. Okay? So what that means, if I have a rational function and I have something that looks like this, okay? What's the degree of my numerator? 2. What's the degree of my denominator? 2. So what I look at is I look at this relationship right here. What is the coefficient in the first one? Good. What's the coefficient in the second? Good. And what's 1 over 1? 1. So my horizontal asymptote in this situation is 1. Okay? Now, when the degree of the numerator of a rational function is less than the degree of the denominator, that's what we just talked about. When the degree of the numerator is less than the degree of the denominator, y equals 0. So that's if I have f of x equals x over x squared minus 2. Okay? In this situation, I have y equals 0, and that's what we just had just a minute ago. In this function right here, because this was degree 1, this was degree 2. So our horizontal asymptote was y equals 0. Now, when the degree of the numerator of a rational function is greater than the degree of the denominator, there is no horizontal asymptote. So if I add x to the third, over x minus 1, there would be no horizontal asymptote. We would have what's called an oblique asymptote, and we're not going to get into that. Okay, so you need to worry about identifying the horizontal asymptote when your degree is 1 less on the top. That's when it's y equals 0. When the degree is the same, it's a relationship. Okay? Can I go to the next screen? Is it okay for me to go to the next screen? Okay. For a rational function, and that p of x over q of x, that just means it's rational, where you've got x in the numerator and x in the denominator. Vertical asymptotes occur at any x values that make the denominator 0. So when you are talking about vertical asymptotes, you are looking at the denominator. You are going to set denominator equal to 0. That's how you find your vertical asymptotes. Okay? The x-axis is the horizontal asymptote when the degree of the numerator is less than the degree of the denominator. So that's our horizontal asymptote. So it's just y equals x when the degree of the numerator is less than the degree of the denominator. Okay? A horizontal asymptote other than the x-axis occurs when the numerator and the denominator have the same degree. And then you are looking at the relationship of leading coefficients. Okay, then we are looking at the relationship of leading coefficients. Okay? Can I go to the next screen? We got one more screen. Okay. Crossing an asymptote. The graph of a rational function never crosses a vertical asymptote. Okay? The function is undefined at the vertical asymptotes. The vertical asymptotes dictate the direction of the graph. Those are super important. Okay? The graph of a rational function might cross a horizontal asymptote, but does not necessarily cross. So it might not. Okay? The horizontal asymptote does not dictate nearly as much as the vertical asymptote does, because you can cross it. Okay? This is never, and this is okay to cross. It doesn't mean it will, but it might. Isn't that lovely? Okay. That's the bulk of what you need to know for your test. Now I'm going to show you one more thing that you might see on homework. And for those of you going into more advanced mathematics, you might also see it. I want us to factor this right here. F of x equals x squared minus 9 over x squared minus 2x minus 3. Okay? I want us to factor that. Okay? So you should be factoring that. Okay, now if I want to find the domain of this, I'm going to set x minus 3 equal to 0, and I'm going to set x plus 1 equal to 0. So x cannot be 3, x cannot be negative 1. Now I am going to do my domain. I'm going to do my domain here. So I'm going to start at negative infinity. Now, the next thing that I put down is negative 1. When you do not draw this out on a number line and you look at this, what are you tempted to put first? The 3. Okay, because that's how I solved it. It doesn't work that way. You've got to put it, the number that you go to it on the number line. That's why I encourage you to do the number line. Okay? Because you have to put the negative 1 first, because that's the smaller number. Then I can do negative 1 to 3. Then I can do 3 to infinity. Okay? So that's my domain. Now, at first glance, what we would do is we would identify our asymptotes as x equals 3 and as x equals negative 1. This would be our vertical. Okay, that's what we would identify our vertical asymptotes at. But what do you notice about the numerator and the denominator? They're not equal to each other. The numerator and the denominator aren't exactly the same, but what do they have in common? Good. They have x minus 3 in common. Oh, yes, for horizontal, you're correct. But look at this right here. So could I do that right there? I could do that. So I want to jump over to the horizontal asymptote. My horizontal asymptote, I have a degree of 2 and I have a degree of 2. So it's going to be the relationship of my coefficients. So what's it going to be? What's my coefficient in the top? What's in front of the x squared? Good. What's in front of the x squared in the bottom? So what's my horizontal asymptote? Good. Okay. Now I want to go back and I want to look at my graph. And I'm particularly interested to see what's going on at my graph at this x equals 3. Because what I think should be happening is I think I should have a vertical asymptote there. Here's my graph. Do I have a vertical asymptote there? I have a vertical asymptote at x equals -1. Do I have a vertical asymptote at x equals 3? I do not. And the reason that I do not is because that x minus 3 shows up in both. Now, is my graph still undefined at 3? Yes, it is. It's still undefined at 3. That's why I have a hole right there. Okay, do you see this right here? That's why I have a hole right there. Then I can see my vertical asymptote. Okay? Now, here, my x is only going to be, or my x-intercept is only going to be when that non-repeated term equals 0. Okay, so I've got x plus 3 equals 0. So what's my x value? Good. So that is where I cross the x-axis. Now that x plus 3 was in the numerator. Okay, so my numerator dictates where I cross the x-axis. Now, do you see here is my y-intercept? Right here. Now, I'm going to mark out everything that has an x in it. Okay? What's left when I mark out everything that's got an x in it? -9 over -3. -9 over -3 is what? It's +3, and that's where I'm crossing the y-intercept. Okay? Now that is mostly for those of you that are moving a little bit further into mathematics, but I did want you to be exposed to that. I wanted you to be able to see it. Okay? And again, on your test, you're looking at being able to identify the domain. You've got to tell me my vertical asymptote, or topes, and you've got to be able to tell me my horizontal asymptotes, or tope. Okay? Okay. Now probably what you need to do is you need to take a picture of this. This is the classwork that you're going to work on for the rest of the class. I wanted to get you out of here by 1:45, but I didn't. Okay? I would encourage you to do that now. Don't wait until Monday night. I would do that now. This is when things all come together. Okay? This is when things all come together.